Uh, we talked about the stress calculations, right? We know how to calculate the stresses associated with the weight of the material. We call that geostatic stresses, right? That has to do with the weight of the soil layers or different layers of the soil that essentially exerts stresses on top of the material. We also talked about the stresses associated with the external load, right? And we call that delta sigma. And that delta sigma has to do with the weight of the structure, the dead load, live load, wind load, earthquake loads, and snow loads, rain loads, things of that sort, right? Also, we have stresses that are exerted by the seepage forces, or the movement of water within a saturated medium, which is a little bit outside of the scope of what we are talking about in our lectures. So we know how to calculate the stresses, right? But you as design engineers, what do you need for the design? When you want to design a structure, you calculate the stresses. Up until this point, in all your courses, you learn how to calculate the stresses. You develop your shear diagrams, bending moment diagrams, right? And what is the other thing that you need to know? You also need to know an indication of the strength of the material, right? Because you calculate your stresses and you want to compare that with something, right? And that would be the strength of the material. You compare these two and see how they are correlated with one another, and you want to make sure that the magnitude of the stresses are small enough that it's not going to result in failure, deformation, or in general localized or general failure of the material. So that's basically the general concept, right? You need to calculate the stresses and you need to determine the strength of the material, right? So for the case of the strength, we have different types of materials that you essentially have different measures of the strength for that. Remember, for instance, from your mechanics of materials, you had steel in tension, right? Remember how you determined the modulus of elasticity of the steel? You basically subject the steel into tensile forces, and you see the necking effect, right? You see the deformation that is basically happening in the middle, and that would be narrowing of that steel. And based on that information, you can figure out what would be the strength of that steel. So for the steel, we look at strength in tension, right? You don't compress the steel. You're interested in the buckling of it. But for the rebars, you essentially subject that to tensile forces. Right? So how about for the concrete? What kind of test do we run for the concrete? You run your unconfined compressive strength test in the lab, right? And it was a strain control test, meaning that you impose a certain amount of deformation per minute. Say, for example, 0.2 inches per minute. That would be the strain rate that you have. And you basically will see at a certain level your material essentially shatters, right? Breaks. It's a brittle material. You don't see the plastic behavior of that specific case, as you see, for instance, for the case of steel. How about for wood? Remember, for the case of wood, you're actually testing the material in bending along the fibers and perpendicular to the fibers of the wood, right? So you basically figure out what are the bending strength of the material. And based on that, you can determine also the modulus of rupture of the material as well, right? So that's what we have for steel, concrete, and wood. How about for soils? Yeah, for soils, it would be a different story. Can I put soil in tension? Right? Remember what the load transfer mechanism was. The load transfer mechanism in particulate soils was related to the friction, right? So you're looking at the interaction of the particles. If I subject the material to tension, you basically will compromise the inner particle contact, and therefore you don't see any strength in that material. In very simple terms, in soils, we don't have the glue, right? In concrete, we do have glue. In asphalt, we do have glue that holds those particles together. In soils, we don't have that, right? Therefore, you cannot have high tensile capacity in soils. All right, so what do we do with soils? We look at shear behavior. And not only as a shear behavior, we're looking at the combination of normal and shear stresses in the material. So that was general overview of what we are going. So for that, we need to figure out what is the shear strength capacity of our soil. And based on that information, we can use that shear capacity in our safety factors, right? Remember we talked about the factor of safety. You just basically figure out what would be a measure of strength, what would be a measure of acting stresses, and then you see the ratio, and then what you do, you have to go and check your specifications, right? You go, for instance, for the foundation of this building, depending on the mode of failure, for instance, for punching shear, TxDOT or Federal Highway tells you that you have a factor of safety of 1.5. You have to maintain a factor of safety of 1.5. Or if you're looking at some other type of structure, you have to basically maintain that factor of safety. So for that, you need to figure out what the loading conditions are, calculate the stresses, and then get an idea of the strength of the material. So this is what we are doing here. So once we figure out what the strength is, our next topic is going to be on settlement calculations, right? Figure out what the stress-strain curve is. The stress-strain curve, on the x-axis you have strain, on the y-axis you have the stresses, and you have your stress-strain curve. The peak of that is going to be the strength of the material. So we calculated the stresses, we figure out what the strength is in this lecture, and then we figure out what the strains are, or deformations are, right? So this is basically where we're going from here. All right, so let's move forward with the general definition that we have for the shear strength of soils. So by definition, shear strength shear strength of soil is the internal resistance of the soil mass that acts against rolling and sliding of the particles against one another. So that's a general definition that we have for the shear strength of soils. And then right now we're going to take a look at some of the failure surfaces and the stability analysis pictures, and we move forward and look at what are the typical theories that we have in order to calculate the shear strength of soils. All right, so in terms of the stability analysis, we have to maintain that factor of safety. We have different types of geostructures. For instance, we have retaining structures. Remember what the definition of the retaining structures were? We talked about retaining structures could be concrete, could be masonry materials that you can build and construct and design to make sure that you don't see the movement of soil beneath them. So those are structures that restrict the movement of soil beneath that structure, that retaining structure. Alright, so it basically has to maintain or resist the strength of our soil. We have, for the case of foundations, notice that the other picture that we have here has to do with the stability beneath the foundation. You want to make sure that the soil underneath this foundation is stiff enough, that has enough load-bearing capacity to resist that foundation. This could be the retaining wall that we talked about. This is the stability of the slopes. We are interested, we want to make sure that that embankment that we have that contains a slope, we want to make sure that that slope will not fail, because it basically moves into the highway, and we want to restrict that. We do have information about the pavement here. You want to make sure that the stresses induced by this wheel load is not going to induce failure in this multi-layer structure. This is a little bit different than the other type of structure that we have, because you have essentially different modulus values in different layers, or different stiffness properties in different layers there. And that's the reason that the nature of contact between these layers are also going to be a factor when you are doing the analysis. And ultimately, we do have tunneling. For instance, if you have buried structures or tunnels in general, you basically also have to make sure that the soil around it and above it is not moving. Otherwise, you're going to see failure in the material. So all of these are called failure surfaces. Failure surfaces or failure planes are planes or surfaces that the magnitude of the stresses exceeds the strength of the material. Does that make sense? So any point along this line basically tells you that the magnitude of the stresses are higher than the strength of the material. And that's the reason that you see the rupture in the system. And notice that we have, for different types of geostructures that we have different failure planes or failure surfaces. They look different from one another. In graduate courses, you see, for instance, for the case of slopes and retaining structures and foundations, you can mathematically calculate the function that the failure surface is going to happen. So that nonlinear surface that you see there, you can mathematically calculate where exactly that happens. Remember in previous lecture we talked about it's not a good idea to have concentration of mass at the top of the slope, such as having a pool at the top of the slope. Imagine if you have a pool right here that basically induces a lot of stresses, and that is in the rupture zone, right? You want to make sure that it is outside of that so it's not going to mobilize the soil along the way. So this was the general reasons for the stability analysis in general. So this is the picture that I took in Dallas area. Notice that we are looking at the slope. That slope is relatively flat at the right of highway, right next to the highway there. But still this slope failed. This is how the failure slope, even in a very shallow and relatively flat slope, looks like. This is the case that the night before they had a lot of rain. And that rain essentially compromised those frictional forces. Even on the very flat slope, you see the failure took place. And again, as you can see, it's a very fine-grained material, right? We're not looking at big chunks of boulders and objects. All right, so we have to maintain that failure in general. So when does the failure happen? When you're looking at normal forces, those are forces that are happening from the top, and then you have horizontal forces or the sliding forces. Now, if the combination of that shearing forces and normal forces reaches a certain number, basically we'll see the movement of the soil particles against one another. And that would be when the failure in the material will take place. And this is an example of what happened in Taiwan a few years ago. And as you can see, the whole slope, and let's call that the whole mountain essentially, moved towards the highway. This one was the case of a combination between earthquake and high moisture content in the soil. So a few days before the earthquake happened, they had a very good rainfall. And then the earthquake happened, and you see all those soil particles essentially slide past one another and fill out this highway here. So this is an example of failure. Obviously it has dire consequences in terms of the life of the people. All right, so let's quickly move forward with our failure surface and the general definitions. The soil grains slide over each other along the failure surface. No crushing of individual particles are assumed. So we are assuming that you don't see the particle crushing here. Everything is associated with the sliding and movement of the particles past one another, or in very simple terms, jeopardizing the frictional forces. Right? At failure, shear stresses along the failure surface, that would be the tau that we have, exceeds the shear strength of the soil. If you isolate this element here and bring it down, and you look at that right outside, this would be the red one is your failure surface. This is your failure surface. And you notice that there is a normal stress, that sigma that we have there, and there is a shear stress in there. The combination of that normal stress and shear stress reached a certain point that the material will fail. We're going to talk about equations and how you can predict that. But let's grasp the concept here and see what happens here. Here we're looking at footing and embankment, or looking at the failure of the slope. Notice that again we do have that failure surfaces there. And failure surface, if you want to write down the general definition there, we also call this one failure plane. the acting stresses exceeds the strength of the soil and results in mobilization of the particles. All right, you can also model these failures also in the lab as well. This is one of our lab models that we have for that embankment and the slope here. And as you add the load at the top and increase the level of saturation of the soil here, you see the failure will take place. And the markings along the line here shows you the failure surface, which very well follows the theory in terms of the failure surfaces that we have. All right, in terms of the failure, you also have to make sure that everything beneath that foundation is also very well intact. For instance, in this specific case, you're looking at the non-homogeneous deformation that we have in that structure. Notice that the other two structures very well stood in their place, right? The other structure failed. Foundation, the outside foundation failed, and as you can see, it crushed the other building. It resulted in the damage of the other building. So this is another issue that we have, especially in congested cities, when land values are of high value. Obviously, you want to make sure that everything is very tightly placed and spaced right by one another. Therefore, any interaction between the two buildings also needs to be considered. Sometimes, especially in very big cities, they build the buildings and attach the buildings right next to one another. So if one small earthquake comes, these two are essentially acting similarly instead of acting as an isolated structure. All right, this would be the definition of the failure surface that we have for the case of retaining a structure. You can see the definition of the retaining structure as we talked about. A retaining wall is a structure designed and constructed to resist the lateral pressure of soil when there is difference in the ground elevation, right? So this is a general concept that we have and the reason that we need to know about the shear strength of the soil. This is a failure of the retaining structure. We talked about the land values and essentially the properties that are oceanfront, or they want to have good views. They want to make sure that they're building right next to the slope there. And that's the reason that you see oftentimes they have 90-degree slopes. That's extremely, extremely dangerous, as we do have in this case. In the graduate course, in the advanced geotech course, and we talked about the case study in San Francisco Bay, when even they used a very relatively flat slope underneath the water, they saw failure. And they used a factor of safety of 1.17, which is extremely low. And that resulted in the general failure of the slope right beneath the bay, and resulted in the failure of the port that was on the other strip of that. So you have to be cognizant of the shear strength of soil when you're looking at the stresses and strains and also the interaction of the particles with one another. All right, so this is a general definition before we move forward and look into the theory in general. So shear failure happens when the soil, when the shear stresses are large enough to make the particles roll and slide past one another. Let's take a look at the right-hand side of this plot. Notice that this rolling and sliding that we see here is a function of both normal stresses and the shear stresses that we have. If you have high magnitude of the normal stresses, the interaction between the particles are going to be more as opposed to less interaction, right? When there is less stresses at the top. Therefore, you have to be mindful of that, and that's the reason that we have a theory that is called Moore-Coulomb theory. All right, so where did you hear about Moore? Moore circle, right? You learned about that in mechanics of materials and also in geology course, right? Also, your TA is going to give you a general overview of what the Moore circle is, but we're going to use that extensively for the shear strength of soil, because we are looking at the Moore-Coulomb failure envelope and see how that is, how you can estimate the strength of the soil and the stability of the soil based on that theory there. All right, so What was the Moore circle, or what was Moore? Right, so remember Moore circle was essentially a graphical method to represent stress transformations. So that was a graphical method to represent the stress transformations. And what does that mean? Remember you had a cube element, or you had, let's call it a square element in 2 dimensions, and then you rotate that by alpha, and you wanted to see what would be the projections of those initial state of the stresses, and you can simply use Moore circle to be able to do those calculations there. So what were the significance of, what are the things that you can extract from the Moore circle? So remember your Moore circle, remind me what the x-axis was, what the y-axis was in the Moore circle.
Stress with your x-axis and your normal stress with your x-axis and your y-axis with your shear.
Yes. As Jeremiah mentioned, you're on the x-axis you have normal stresses, and on the y-axis you have the shear stresses. And then you had your half circle or full circle that we had because it was symmetrical, we go half circle, right? And then you have sigma vertical and sigma horizontal, right? Those are sitting on the x-axis, right? And also you had the definition of principal stresses there. What were the principal stresses?
They were basically one on the x-axis when you go here.
Remember you had your tau here, you had your sigma here, and then you had your square element, if you will. Remember this one was sigma 1, this one was sigma 3. Typically in geotechnical engineering we call sigma 3 as confining pressure. That's essentially the pressure that holds the particles together. That's the reason we call it confining pressure. And sigma 1 is your vertical stresses. Alright, what do you have here? You have a center here. What was the definition of center? Or how do you calculate the center? Do you agree with that? This is your center here. This is sigma 1 plus sigma 3 divided by 2. How about the radius of the Moore circle? Agree? In geotechnical engineering, we call sigma 1 minus sigma 3 as sigma d, or deviatoric stress. Basically the deviation from the 2 stresses that. Alright, we talked about the principal plane. What is a principal plane? Let's go one step back. What is a principal stress? Principal plane is the plane on which the shear stresses are 0. Remember you have your cube element, you have the shear stresses in there. Now, if you can find a rotation that has 0 shear stresses, we call that principal plane. So the principal plane, where is the principal plane? Where is shear stress 0? The x-axis, right? The shear stress is 0 right here. Therefore, your sigma 1 and sigma 3 are principal stresses. Notice that I didn't put any shear stresses here all around it. So this element is free of shear. The stresses are principal stresses. So principal stresses are the stresses that are happening on the principal plane, and principal plane is the plane on which the shear stresses are 0. Right? So that's coming from your Moore circle. So that was a quick review of what that Moore circle was. And this circle essentially at any point along which it gives you the combination of that rotation of the cube that we have. Right? So any point represents a rotation in the general form of the equation there. Alright, so let's talk about the Moore-Coulomb failure criterion for the calculation of shear strength of soil. Alright, so let's talk about the contribution of each of these gentlemen in the Moore-Coulomb failure envelope. Alright, where did we see Moore? In the Moore circle, right? That was the stress transformations in the graphical format, right? We know what the C is, the center is, what the radius of this circle is, and things of that sort. You can calculate the principal plane, the plane of maximum shear stresses, the plane of maximum normal stresses, and everything that you can get from your Moore circle. Alright, so that was one of the contribution of Moore. Alright. Let's start with the general concept. More developed. Alright, Moore developed a methodology for the characterization of rupture or failure of geomaterials. He stated that the soil fails due to critical combination of normal and shear stresses. Not just normal stress and not just shear stress. A critical combination of the two. So essentially he said that tau sub F, which is the shear strength of soil, is a function of the stresses that we have. So this is your shear strength. Or stresses on failure plane. What was the failure plane? The plane on which the magnitude of the stresses are higher than the strength of the material. Right? So what does this equation look like? So you have a nonlinear function here, right? This is your tau on the y-axis, and you have the normal stresses and also the combination of the stresses that you have that are happening on the x-axis. Alright, so this was the contribution of Moore. Now let's see what Coulomb said here. you basically said that the nonlinear function that we have, the tau equals to f sigma ij, can be approximated with a linear function. Alright, so let's talk about that linear function. I intentionally go slow